This video shows how to solve ordinary differential equations, or ODEs. We're going to be solving that in Python. We'll do it with the ODEINT function. What we'll do is problem number 1 will just be a single ordinary differential equation. Problem 2 will be 2 ODEs, and then problem 3 we'll try with 4 ODEs. So if you'd like to go to the examples for this problem, come to the course website at CHE263 at APMonitor.com, and then come down to the homework on the right, and we're going to be doing homework number 16 right here. So if you want to see a PDF version of it, there it is, or if you want to just grab the file for it, I downloaded that, and so let me go to my downloads folder and go ahead and retrieve that over here, extract it, and I'll just run it off of my desktop. Okay, so I'm going to open up IPython and the notebook, and then let's go ahead and start going through this. Okay, so we have, once that opens up, I'll go to my desktop and then to homework 16 and open up this IPython notebook. Okay, so here's the problem. We'll go ahead and do the first one. We want to solve the this ODE to time equals 6. And we'll plot the results of the function y of t. The initial condition is y naught equals 1. Alright, so the first thing that we need to do, kind of preliminary stuff, maybe at the beginning of this, let's go ahead and insert a cell above. We'll just load some of the packages that we're going to need here. I'll do import numpy as np. We'll do from Scipy.Integrate. We'll import the ODEINT, or the ODE integration package, and then let's go ahead and do matplotlib as well. We need to do the matplotlib inline if we're using IPython. If not, don't use that one. And then we'll import matplotlib.pyplot as plt. Okay, so go ahead and run that right at the beginning. It'll import all of those packages for you, and then we can start using them like down here. Okay, so first of all, what we want to do is define a new function. I'll do function of y and t, and that is going to return dy dt. And I'll just put, you got to put the derivative, you got to assign the derivative value, return that to the solver, and this side is going to be what is the derivative equal to. So that's going to be numpy exp negative t, and then we'll return dy dt. Okay, so to use the ODE integration function, let's go ahead and just do y equals ODEINT, do our function name, we do the initial value, and then we do the times that we want to solve at. Okay, so we can do 0, 0.1, 0.2, 0.5, something like that, and then print y. Okay, so there are our values right there. But let's say we want to come up with quite a few more values. So this is our initial condition is 1.0. Let me go ahead and just put that in as initial condition. Let's come up with some more times that we want to see this at. I'll use the numpy linspace between 0 and 6, okay, and then go ahead and put that in as the time, and then we get some more y values. Okay, so we get a lot of y values, but let's say we want to see that graphically instead. Let's go ahead and create a new plot, and we'll do t comma y. And I'll do, let's see, an X label, we'll say that's time in seconds, and then also a Y label, and that will be Y of t. Okay, so let's run that again. There's our plot, Y of t versus time. Okay, so there we have the solution to problem number 1. That was this ordinary differential equation, initial condition equals 1. Now let's go on to the second problem. This next problem is going to have, this one's going to have 2 differential equations. Okay, so we have, in part A, we've got to make a plot of CA versus time, and then in part B we've got to do CB versus time. Okay, so let me go ahead and just create the A versus time for part A, and let's just do just like we did for the last one. We'll go ahead and create integrate it, and then we'll plot it. Okay, so we want to create a new function. In this case, I'll say it's going to be reaction and C and time. I'm going to pass in two values here. That's going to be concentration of A and concentration of B. So let me just go ahead and write those out. Concentration of B is going to be the second one. Okay, and then let's get a K value in there as well, is equal to 2. And then I'll do dA dt is going to be equal to negative K times CA. Okay, let me scroll down just a little bit there. Okay, CA and then dB dt. Okay, you put the differential. You basically got to evaluate what are my differentials here. Differential values, and then that's going to go back to, we're going to return those. Okay, so I'll go ahead and return this dA dt, comma dB dt. Okay, so we'll return that. If we just want to evaluate it, let's say we want to print it at, let's say values of these concentrations and a time of 0.5. Okay, let's see, that says invalid syntax. I'm missing a parentheses there. Okay, so it gives me my derivative values, but now we're going to give that to an integrator, and then the integrator is going to determine all of the values of concentration of A and B over a certain time period. So like we did in the last example, let's go ahead and just create some new times that we want to look at these values at. Do 100 points between 0 and 5, and our initial concentrations, let's say those are 1 and 0. Okay, and then our final concentrations, we're going to use the ODE integrator function, and we have our reaction, and then initial conditions and time. Okay, so that's all we need to do to get the concentrations. Now we're just going to visualize those with a couple plots. Okay, so let's do time and concentration. Take the first column, that's going to be the A, and we'll do a red dashed line. Let's say I want to make the line width just a little bit bigger. I'll say that equals a 2. Okay, go ahead and copy this, and let's just do column 2 now, and I'll make that a blue line. Okay, so now we can see it. Let's just go ahead and add a couple things to this as well. We'll do an X label, and that'll be time, maybe in seconds, and then we'll also do a Y label, and let's say that's concentration. And let's give ourselves a label, a legend as well. Okay, legend, and CA and CB. Okay, so there's our final plot right there. If I just wanted to do A, I just plot the A first, but I added this second differential equation right here. So you could get away with, if you just wanted to do this differential equation first, then it would just be, you just have one value of C coming in. Just comment that out, and then just return dA dt. Okay, but since we're going to be returning two of them, the B as well, we'll just go ahead and leave that in there. Okay, so there is our second one. Okay, let's go down to problem 3 now. Now we have 4 differential equations, and this one's just a little bit trickier because we have this reaction network. Okay, so let's just go ahead and copy this. Okay, there's our problem 3, and I'll go ahead and copy it. Let's bring it back over here and just derive some of these equations. Okay, so we have these now. We've got a couple equations that we've got to solve. This is going to be 4 differential equations. You kind of got to know how to do these. I'll just do dA dt. That's going to be negative K1 times the concentration of A times the concentration of B. Okay, and then our B is going to equal, okay, let's see, we have this reaction network here that I'm looking at. It's consumed there and there. So this one's going to be minus K1 Ca Cb, and then we're also going to have a minus K2, and that's going to be times Cb times concentration of C. Alright, let's go on to the next one, which is going to be C. Okay, it appears here and there. So that's going to be equal to, you know how this was negative here, that's just going to be the positive of that. Okay, so the positive, and then Ca, Cb, and then let's see, we're going to have, let's see, we're also going to minus K2 Cb Cc, and then a final one, which is going to be equal to, let's see, that's going to be equal to D, and that is going to be equal to K2 Cb Cc. Okay, so we've got our differential equations. Now we just got to program those, and then we'll plot them. Okay, so we have all of these. Let's come back to our Python, and we'll just define a new reaction. Okay, and that will be a function of z and t, and we'll do k1 equals 1, and then k2 equals 1.5. And let me make this just a little bit smaller so we can see it over here. All of these equations that we just derived. And okay, so we'll do dA dt, and that's going to be equal to negative k1 times, this will be z0, that'll be our first element, and then z1 is our second, that's going to be b. And then let's do dB dt, and I'll just go ahead and copy this first one right here, and you know what, I can actually make this just a little bit easier. So reaction 1 is going to be equal to this k1 times that, and then reaction 2 is going to be k2. The reaction rate of 2 is going to be k2 times z1 times z2. Okay, so that's going to be minus reaction 1 minus reaction 1, and then we had minus reaction 2. Okay, and then dC dt, okay, that's going to be plus reaction 1 minus reaction 2, and then ddt, that's going to be plus reaction 2. Okay, so there are reactions and the different differential equations, and then we just have to return all four of those. So dA dt, dB dt, dC dt, and dD dt. Okay, so these four. And so we've returned those. Now we can write our ODE integrator. If we want to go from, in this case we needed to go from, let's see, 0 to 3 seconds. Make that a little bit bigger now, 0 to 3 seconds in increments of 0.5. So one way to do that is to do the, it's called the aRange function. Okay, so aRange, or you can use the linspace as well. So if you use the linspace, you got to tell it how many increments to use. aRange is nice because that one will allow you to specify actually the increment that you're going to use instead of the just the linspace, which is just, so if we came over to let me come over here. So linspace, you have 3 arguments here, or 2 optionally. You just go start, end. Okay, and then if you wanted to put in the 0.5 increments, you might need to do, I think it's 16, I believe. Okay, no, this is 0.5. Let's see, what did I say on this? 0.2 increments. Okay, or you can use the aRange, and then you can go from 0, and then you got to do like just a little bit over that. Okay, you can do 3.01 and then do increments of 0.5, and then it'll give you that as well. Okay, so let's try. Let me come back here. Looks like my keyboard just stopped working. Let me see if I can get that to reset on this surface. Okay, I don't know why that's... Sometimes the browser is a little bit funny here. Let me try the different browser here. I'm just going to switch over here. Okay, make sure that one is saved before I come over. Okay, so I'm back over into Firefox. Let me just try this in Firefox instead. Okay, there it is. Somehow the Internet Explorer browser, the new Microsoft browser, wasn't quite working right. Okay, so 0 to 3.01, I'll do 0.2. Okay, let me just go ahead and print t there just so I can show you it's going in increments of 0.2. Okay, and now let's go ahead and just define our initial conditions. Okay, and we'll just say that is going to be 1, 1, 0, 0, and then we'll do our concentration is going to be equal to this ODE integration function, and we will do, let's see, this is going to be reaction, and then Z0 and T. Okay, so we've got this thing calculated. Now we just need to display it. Sometimes it's easier just to say CA equals, just parse it out right here so you don't have to do it later. We'll do 0 and A, B, C. Let's do the B, C, and D. Okay, so that's going to be 1, 2, and 3. Okay, now we also need to compute the selectivity as well. That's going to be equal to C divided by C plus D. Okay, so you can see that right there in the middle. It's C over C plus D. Let's go do the selectivity as well. But if we just do selectivity equals concentration of C divided by concentration of C, let's see, overwrite. Okay, let me close this one in here. Concentration of C plus concentration of D. Okay, then I'm going to divide by 0, so I don't like that. I want to maybe put a, let me just go and create a blank array here. Empty of length C, C. Okay, and then we'll do a for loop for I in range, this length of the C value, and then we'll say if the absolute value of Ci plus C di is greater than 1e to the minus 10th. Okay, so if it's basically greater than 0, then we'll go ahead and do this division thing right here and just define it at each element. Okay, so we'll do I and then I here as well. Compute that. Else we'll just say that Si equals 1. Okay, so we've got those. Let's see if we get that error. Again, we don't. Okay, so now we can go ahead and plot it. Okay, so we're going to do PLT plot, and we'll do T versus concentration of A, and let's do a red line, or a red dashed. Okay, you can just leave those out and it'll do the default. It'll change the colors for you. Okay, let's just leave them out just for the sake of time here. Let me copy these two and do C and D, and we'll do one more plot. We'll do S as well. Okay, on that same one, and then okay, so let's look at those. Okay, great, different colors, you can see those. The other thing you can do, one of the nice things is you can do save fig if you want to do like results.png. You can save those. If you go back to your directory, okay, so you can see this results.png that was saved right there. So you can save it like for a PowerPoint or a presentation that you want to give. You can save it there. Okay, but you might want to just make this just a little bit prettier with some X labels, Y labels, add a legend, things like that. Okay, so that concludes this tutorial. We did one differential equation here in problem 1, we did 2 in problem 2, and then we did 4 differential equations in problem 3 in Python.